Okay, this is one of the hardest questions I think I've seen for an infinite geometric series. It is really difficult. You may need to go through this a number of times to really understand it. It starts off with giving you a view of looking at certain functions. So we've got observed that 1 is equal to 1, 3x can be split up to x plus x 2x, 5x squared can be split up as x squared plus 2x squared, 7x cubed can be split up that way, and 9x to the power of 4 similarly that way. So what we want to do is use all these to find a limiting sum of that series. Now, if we look at it as we go along, we're not seeing a geometric series to start off with. Now that's the problem. Is like, wait on, if it's going to be a limiting sum of a series, don't we need to see something that's a geometric series? So there's the trick. We need to bring in this part here. So, and have a look at, you've got 1, 3x, 5x squared, 7x cubed, 9x power 4. So you can start to see that, yeah, there is a pattern that's starting to occur, but it goes on forever. So that's the trick we want to look at here. So we look at what we've got. There's our expression. There's all our expansions we want. We want to play around with this part here. Now, if I have a look, what I want to do is sum down the columns here, because I'm adding all the left hand side, which means everything on the right hand side is being added together as well. So we're summing down this column. So there's our first one here, that first column. There's the 1 plus x squared plus x cubed and so on. And again, it goes on forever. The next one, we've got 2x, 2x squared, 3x, 2x cubed and so on. So we've got 2 outside of the x plus x squared plus x cubed and so on. And then the next one starts at x squared. So 2x cubed, 2x power 4. And then it goes on forever. It keeps going. Like everything goes on, and it goes on until it doesn't stop. So what we want to do is then look at this and go, well, now if I look at these, I've got geometric progression in all of those. So 1x, x squared, that's a geometric progression. Goes on forever. X squared, x cubed, and so on. X squared, x cubed, x to the power of 4, and so on. That one will start at x cubed. The next one will start at x to the power of 4, and it keeps going on forever. It will keep going that same pattern. Now, if it's going to be they want us to find an infinite series, so must be assuming that our common ratios are between -1 and 1. So if that's the case, this geometric series here has a common ratio of x and a first term of 1. So that's where we get the a on 1 minus r. All these other ones have 2 out the front, so that's where that 2 comes from. But if we look at this, x plus x squared plus x cubed and goes on. So we've got a first term of x and then a common ratio of 1 on x. This one has a first term of x squared, common ratio of x. The next one has a first term of x cubed, common ratio of x. So it looks like that. So using that a on 1 minus r formula. But then again, that goes on forever. This is no good if we've got this idea that it's going to go on forever. We need to come up with an expression that's going to give us the limiting sum. So what we do realise though is if we look at this series now, x on 1 minus x, x squared on 1 minus x, x cubed on 1 minus x is a geometric progression as well, because it's in a common ratio of x, okay, which is, so the first term is x on 1 minus x, so that's our a, and the common ratio is just x, because we multiply this one by x to go to the next term. That's where we get the 1 minus x. So divide that one by 1 minus x gives us the 2 times the x from that part, and 1 minus x all squared. To simplify it, we need to get a common denominator for our fraction, so multiply that by 1 minus x on top and bottom, and then we can collect we've got the same denominator, so we can collect our numerators. It gives us 1 minus x plus 2x gives us 1 plus x over 1 minus x all squared. And that's our limiting sum. That's an expression for the limiting sum. Not easy. Go through it again. Be really careful with it. It's just multiple series geometric progressions that allows us to once we arrange them, allows us to get a number of limiting sums to break it down and get a expression that we needed. Question 9, a little bit easier. So we've got a second term of the geometric series is 120, fifth term is 50.625. So we want to play around with this one. Firstly, we'll find the common ratio in the first term of the series. So similarly to what we've done before, A times R is equal to 120. So A is 120 over R. And A times R to the power of 4 would be 50.625. So again, we can go and solve it. 120 on R times R to the power of 4 would equal to 50.625. Do some cancelling. Divide by 120. Gives us nice values of 27 over 64. Cube root of that would give us 3/4. So if that's 3/4, A is 120 divided by 3/4, which is 160. Next step we want to do is find the limiting sum. Well, we've got A and R. We substitute into the formula. 60 over 1 minus 3/4 gives us 640 as the limiting sum of this geometric series, because R is going to be 3/4. So the terms are getting larger, but they're not getting that much. Well, the terms are actually getting smaller as we go along because they're multiplying by 3/4. The sum's getting larger, but it's going to be stopping at 640. It's going to be getting close to 640. As we start to see here, because in part 3 says find the sum to 40 terms. So we go and apply that formula. A outside of 1 minus R to the power of n over 1 minus R starts to give us 639.999, and we get that. Subtract that from 640. So the sum to infinity minus the sum of 40 terms gives us 6.4 times 10 to the power of minus 3. We have to answer in scientific notation because it's starting to get really small, as you can see. That's really close to 640. So we're dealing with scientific notation to solve this. Okay, and that's the only way we're going to be able to express our difference, is going to scientific notation, because our terms are just getting so close to 640.